Thank you, Ivana. The title of this short presentation is High Performance Green Electronics Using Resource Efficient Printing Route. But before I start, I would like to bring this put the context or background. If you look at conventional CMOS production today, it's inherently and unavoidably wasteful. As IC fabs, they mostly rely on subtractive manufacturing methods. If you look at the wastage levels, it jumped in 2013 when fabs adopted double patterning techniques. And since then, we see a lot of pollutants going into the wastewater. Conventional IC manufacturing consumes vast quantities of water. And as an example, in 2020, TSMC sourced 77 million metric ton from strategically located reservoirs, which is equivalent to 6,200 liters per wafer. They also are major consumers of energy. Again, taking an example of TSMC, it alone consumed 16,000 gigawatt hour of electrical energy, which is enough to power every household in Scotland for more than 20 months. And the UK is second largest producer of electronic waste in the world and one of the largest exporters of electronic waste. With this context, I would move to the next slide, which talks about lots of applications that we come across today, which is about distributed sensing, IoT, smart cities, etc., interactive systems. That's somewhere on the top right of the slide. And most of these require high performance. So there is a kind of, in terms of what we need is high performance. What we have in terms of producing the devices for high performance is something, a wasteful process. And then this raises question, what can we do to achieve high performance at using methods that are less wasteful or zero, that produce zero waste? In that regard, two techniques that have recently been explored. One is transfer printing. On the left-hand side, you see these as the process key steps of the transfer printing. And on the right-hand side is the context printing. There have been various, all over the world, several researchers are exploring these two techniques. We have also been exploring in Best Group in Glasgow these techniques, but these have been modified to align with the green IC process. Coming to the first technique is this transfer printing. This animation shows what transfer printing looks like. So you basically realize micro nanostructures on the wafer, carry out all high temperature processing steps on the wafer, and then using an elastomeric stamp, you pick the structures and transfer them onto flexible substrate, and this can be transferred over large area. This way you can also overcome the traditional bottlenecks of the conventional IC fabrication, that is, it is restricted to the wafer size. You can go to large area, and it is resource efficient in a sense that you are using only the wires or small layer of these wafer, and that can be repeated. This process can be repeated to realize electronics over much bigger area. But the problem with these technique is that it's simply, in simple terms, it's a pick and place technique, and it leads to elastomer has a problem. This leads to, because of the softness itself, it leads to poor registration. There's a poor yield, and the process is not always repeatable. And there is an issue of contamination, because normally elastomer is PDMS, and there's small residues, they are left on the nano ribbons. And because PDMS is also an insulator, realizing transistors from this type of approach can be difficult if there are residues left on the ribbons. To overcome this and to also increase the speed of manufacturing, we developed this direct roll printing technique, which essentially you have the micro nanostructures on the wafer. That's 9 centimeter square sample that you see here. We have developed this setup in Glasgow, and this is, we call direct roll printing. This is the substrate on which you transfer the nanostructures. When certain force reaches, the roll will start. You can see the side view here on the bottom right. And once it is done, the wires are lifted from the donor and they are transferred to the receiver substrate. Now that's a direct process. There's no need for PDMS in this case. And in reducing number of steps, reducing number of the amount of materials you are using, you are also creating a resource efficient process. Further processing by printing metal lines, source and drain, we also got the devices, and we have got both N-type and P-type device in this case. The transfer characteristics are shown here, PMOS on the left-hand side, NMOS on the right-hand side, and this table at the bottom compares these performance. Now, the lower row, which talks about mobility, says PMOS is about 200 centimeter is the per volt second, and NMOS is about 600. Now, these are at par with conventional fabrication that we have, and this means this is a good example of printing using printing route, a resource efficient route to develop electronics that can have performance at par with the IC, conventional IC. And this is, we are extending this approach now to develop green ICs. We also, the approach is versatile in a sense that you can you can use this approach over different substrates. This slide shows copper foil, PET substrate, then you have aluminum and magnesium foil, and then transparent polyamide, etc. And in all cases, we noted that the transfer is good, yield is also great. And also we tested the feasibility of approach over large area. You can see these are these small dots that you see, they are nanoribbons, and this zoomed version is shown on the inset. And likewise on the right hand side, they are transferred on flexible substrates, the same structure. We also compared this approach with other approaches that have been reported in literature, and we noted that direct roll printing, that is at the bottom shown here, it has less complexity, yield is more than 95%, and excellent registration, which is less than 100 nanometer, that has not been achieved so far. This has been one of the problems with printed electronics. So with high registration, we can think about going on large area. The second technique is the contact printing technique. In this case, what we do is we grow nanowires using a bottom-up approach. And once you grow the nanowires, you bring them in contact with the receiver substrate. And at certain pressure, you slide the donor substrate or receiver substrate, which leads to transfer of wires on the receiver substrate. And that leads to ultra-thin electronic layer on which you can further realize the transistors using printed metal lines or printed dielectrics, etc. Again, to realize this thing, we have developed in my group here in Glasgow, we have developed this automated setup, which is shown here in this video. So basically what it does, it says self-alignment. So that's the donor substrate, that's the receiver substrate. They are aligned. When certain pressure is reached, the sliding starts. And once you have the sliding is over, you have wires transferred on the receiver substrate, and same image was also shown here. So you can repeat this process for large area as well. In this case, the electronic layer based on nanowires is on 14 millimeter by 9 millimeter, and we process this further to get various devices. One example is shown here as a photo detector. So the zinc oxide nanowires and silicon nanowires, they were transferred on polyamide substrates. Zinc oxide nanowire was used here as a photo detector, and rest of the wires were used as a resistor. So that way we are able to develop various sensors and using these nanowires as well as transistors. And this takes us a step closer to systems that we can develop using roll-to-roll nanowire printing, eventually leading to a device or let's say based on the circuit, developing devices using this process. And one example of one transistor, one memristor is shown here, as well as the electronic skin, which will have the nanowire based printed circuit at the back plane, covered with the transducer layer on the top. Some of these transistors on the back plane will act as a readout or signal conditioning, whereas others can be a transistor based pressure sensor using either a variable resistor in the source drain line, or you'll be using a variable capacitor over the gate. Well, that brings me to the end. I would like to conclude by saying that sustainable IC fabrication is needed and can be achieved by significantly reducing materials, water, energy consumption, while minimizing environmental impact of end-of-life products. For example, by using recyclable and biodegradable materials. Some of these were presented by previous speaker. Printed electronics, including sensing, is a promising, cost-effective, and eco-friendly route for manufacturing high-performance electronics on various substrates, including those having flexible form factors. And high-performance printed electronics, in my view, is a disruptive route that will add new dimension to the electronics industry, which is currently focused on miniaturization, still focused on miniaturization. And with careful selection of materials, such as biodegradable materials or simply degradable materials, it will be possible to develop green ICs, which will degrade at the end of life and thus help us address the growing issue of electronic waste too. And this also aligns with UK government as well as other governments' policy. In our case, it's net zero policy and environmental safety, health, and sustainability objectives, which are prescribed by the International Roadmap for Devices and System. I would like to acknowledge the printed electronics theme of my group, Best Group, as well as funding from EPSRC, and some funding also came from European Union for this research. Well, that brings me to the end. Thank you very much.